Even if you've written the best in class Spark code, your job may take forever to complete if you've not done the allocation of CPU and memory resources correctly. Hey everyone, welcome back. In this video, we are going to talk about executor tuning. Basically, how do you decide the number of executors that you should create and the amount of memory and the number of cores that you should be allotting to those executors? So let's first have a look at how executors are created and how executors would look like inside a node. So here I've taken one node, and one node is basically one machine in a cluster, and you could have several of these machines in the cluster. And the configuration of this machine is that it has 17 cores and it has 20 gigabytes of RAM. Now let's say you want to do a Spark submit, and when we do a Spark submit, we basically specify the number of executors we want to create, the amount of cores, and the amount of memory that we want to allot to those executors, right? So let's go ahead and create three executors. Let's go ahead and create three executors, and let's say that I have assigned 5 cores and 6 gigabytes of RAM to each of these executors. So in total, you would end up using 5 into 3, which is 15 cores, and 6 into 3, which is 18 gigabytes of RAM from the whole cluster. Yeah, and this is how your executors would look like. So this executor, you would have 3 executors. You would end up having 3 executors, and each of them would have 5 cores and 6 gigabytes of RAM. 5 cores and 6 gigabytes of RAM. Yeah. So here we saw that inside a node, this is how you're going to create executors during Spark Submit. Yeah. But again, whatever number I assigned over here, right, this was based on my wishful thinking, right? There are, of course, certain logic and certain rules that you would need to follow in order to optimally size these executors, in order to optimally decide what are the number of executors you should create and how much memory and how much cores you should allot to those executors. Yeah. So let's imagine you had to create and run a Spark job. How would you decide what are the number of executors, what are the number of executors and the cores and memory that you would assign to those executors, right? A very critical question. So let's go ahead and take a few examples in order to understand how we would do that. Okay, so let's say you have this cluster and you have the following configuration. You have the following configuration. So let's say you have 5 nodes, which is 5 different machines, and each of those machines have this configuration. They have 12 cores and 48 GB of RAM. Yeah. So basically you have 5 machines in a cluster. You have 5 machines, and each of those machines have 12 cores and 48 GB of RAM. Now the question is, how do you decide the number of executors, that you should create when running a Spark job, the cores per executor, and the memory per executor? Yeah. So there is a way to think about this. So you would naturally have 3 options as we see over here. The first option would be thin executors, the other one would be fat executors, and the last one would be optimally sized executors. Of course, by looking at this, we would always want to go ahead with optimally sized executors, right? But all three of them have advantages and disadvantages of their own. So let's first have a look at fat executors. If you were to create fat executors, how would the configuration look like, and what kind of benefits or benefits and disadvantages that it would have? Yeah. So let me just move my camera over here, and let's go ahead and perform the calculation, right? So first of all, what are fat executors, right? What are fat executors? So fat executors are those executors which occupy a large portion of the resources on a node. Yeah. So simply, to keep it simply, fat executors are those executors which occupy a large portion of the resources on a node. Yeah. So here we have 12 core, 12 core and 48 GB of RAM. So fat executors are going to occupy a good portion of these resources. Yeah. So now let's go ahead and do some calculation. So in order to calculate the number of executors and the cores and all of that, we are first going to leave out one core and 1 GB of RAM for operating system, Hadoop and Yarn and other processes, right? So per node, we are going to leave out one core and 1 GB of RAM. So that is the first thing that we should do. So if we had 12 cores and 48 GB of RAM, we just subtract one. We just subtract one, and what we are going to get is the number that we have over here. So this is per node you're going to have 11 cores and 47 GB of RAM. Yeah. So now what we said, that fat executors are going to occupy a large portion of the resources. Yeah. So what we are going to say is one fat executor will take all of 11 cores, and it is going to take all of 47 GB of RAM. So this simply means that one node is simply going to have one executor. It is going to have one executor which takes up all of the 11 cores and 47 GB of RAM, and this much amount of space is left for the operating system and other processes. Yeah. So this would simply mean now that one node has one executor, and our cluster has 5 nodes, as you've seen over here. So one cluster has 5 nodes. So 5 nodes are going to simply have 5 executors. So we are going to have 5 executors. Now the number of executors, is simply going to be 5, and executor cores, how much is it going to be? Take a guess. It is going to be 11. We already decided that over here. Yeah. So it is going to be 11, and executor memory is going to be 47 gigabytes over here. So this configuration is the configuration that we supply when we do a Spark submit when we are creating a job. Yeah. So basically, if we were to use fat executor, we are going to have 5 fat executors. Yeah. One present on each of the nodes. And you see that these are very strong, very powerful executors, because each of them has 11 cores and 47 gigabytes of RAM. Yeah. So you're going to end up with 5 executors, each having 11 cores and 47 gigabytes of RAM. So this is how the scenario would look like for fat executors. Now let's have a look at thin executors. So first of all, what are thin executors? Thin executors are just the opposite of fat executors. Thin executors occupy minimal resources from the node. Yeah. So they would occupy minimal resources from the node. So let's quickly do a few calculations. So here we've seen that we've already left out one core and 1 GB of RAM. So per node, again, we are left with 11 cores and 47 gigabytes of RAM. Yeah, so one node has 11 cores and 47 gigabytes of RAM. Now what we decide is that one executor, because it contains minimal, it takes up minimal resources, I'm going to only give it one core. One executor is only going to take up one core, and we have 11 cores, so this simply means that one node is going to end up with 11 executors. Yeah, simple unitary method. We have one core per executor, and there are 11 cores in total, so there are going to be 11 executors. Yeah, now what is the memory per executor? What is the memory per executor? So we know that we have 11 executors in total, and 47 gigabytes of RAM is all that I have on node. So 47 is my total RAM, and in one node I have 11 executors. So this is somewhere going to be 4 gigabytes. Yeah. So what we've essentially found out here is one executor is going to contain one core and 4 gigabyte of RAM. Yeah. Now the last thing that we need to find out is what is the total number of cores, and that is very simple to find out. So one node has 11 executors as we've seen over here, and we have a total of 5 nodes. So this simply means we are going to end up with 55 executors. 11 into 5 is 55. So again, the configuration is going to look something like this. Num executors is going to be 55. The executor cores, the executor core is going to be 1, and the executor memory is going to be close to 4 gigabyte. Yeah, so this is how the configuration is going to look like for a thin and a fat executor. Now let's understand the differences, the advantages and the disadvantages for each of them, and then we would go ahead and understand how an optimally sized executor would look like. Okay, so now let's have a look at the advantages of a fat executor. So the first advantage of it is increased parallelism. So we've seen that fat executors are pretty powerful. They have a lot of cores and a lot of memory. So they'll be able to crunch a lot of data, right? So if you have a lot of cores, that means that you'll be able to run a lot of tasks, right? And because many cores are present on one executor, many tasks can be run together, thereby increasing the parallelism, right? Now it is of course very beneficial because it allows you to load data which requires significant amount of memory. So tasks that require significant amount of memory can be easily consumed and processed by fat executors. Another advantage of it is if managing a lot of executors is a concern in any case, right? We've seen that node one node only has one executor, and similarly all the other nodes would only have one executor, either one or minimal executor. So in cases where managing executors is a concern, you could think of fat executors. Now the other advantage is enhanced data locality. Now given that the executor already has a large memory, it is going to be able to fit a lot of partitions in this memory, right? So that would mean that the data it wants to process is already local to it, it's already loaded in memory, right? So it wouldn't need to shuffle data from the other nodes or in the clusters, right? So it is for that reason that the data locality is enhanced, and this overall reduces the network traffic and the overall application piece. First of all, because you don't need to move data across the cluster, right? And because of this, it improves the overall application speed. Now, coming over to the disadvantages, of course, we have a lot of resources within an executor. If we don't fully utilize it, we are going to end up pay for resources which are sitting idle, for resources which you're not even using, right? The second one is fault tolerance. So let's imagine that you have two executors and these reside on node 1 and node 2, and these two executors are crunching a lot of data. So let's say they are crunching 32 gigabytes and 32 gigabytes of data, right? Now let's say for whatever reason this executor failed, something happened and this executor crashed. The amount of computation, the amount of effort that needs to be done in order to recompute this is going to be large, because it was processing a huge amount of data. It was processing 32 gigabytes of data. So there is going to be a good amount of time in terms of computation that is going to be lost in order to recompute this size of data, right? And this is going to reduce the application reliability. Now the last one is HDFS throughput. So for those of you using HDFS throughput simply means the rate at which you can write data to HDFS, or the rate at which you can read data from HDFS, right? Write data to HDFS or read data from HDFS, and the rate at which you can do these two is called HDFS throughput. Now if you use a lot of cores, basically more than 3 to 5 cores, actually more than 5 cores, then this is going to cause a lot of garbage collection. And I've discussed about garbage collection in my previous video on Spark memory management. So if you've not watched it, please go ahead and watch it. So it is going to cause a lot of garbage collection, and garbage collection is basically a process within the JVM in which in which it cleans up your memory for unwanted objects, right? So if your memory is full, it basically cleans up your memory of the unwanted objects, and during this time it pauses your program. So it pauses your program, cleans up the memory for unwanted objects, and then resumes back your program. Now imagine if this is going to happen, this pause is going to happen again and again and again. It is going to take a performance toll on your program, right? So that is one of the reasons why you're recommended to have something between 3 to 5 executors. So these are some of the advantages and disadvantages of fat executors. Yeah. Okay, so now let's talk about the advantages and disadvantages of thin executors. So the first advantage is increased parallelism again, and this might confuse you a little bit because you saw increased parallelism for fat executors as well. But this is a little different, right? In the sense that you would have a lot of executors, right? You would have a lot of executors. So this is basically executor level parallelism. The last one was task level parallelism. In one executor, you had a lot of cores, right? So each core is capable of processing one task, and you can process many of such tasks in parallel. So it was task level parallelism, but this is executor level parallelism, and that's how it's different. So the advantage of it is that you would still be able to process a lot of things parallelly, but these jobs need to be lightweight. The amount of work that each executor is doing needs to be lightweight, because you cannot stuff in a lot of memory, because these guys have very small memory. So you can still do lightweight jobs, yeah, lightweight task. Now The second advantage of it is fault tolerance. So we've seen earlier that one executor was processing a huge amount of data, and then that worker crashed for some reason, and because of that you lost a huge amount of data on which already computation had happened. But in this case your executors are very small, right? So even if you lose an executor, it is easy to be able to recompute whatever has been done over here already. Yeah. So the fault tolerance is pretty good when comparing it to fat executor. Now the disadvantage is high network traffic. Now because this executor has a very small memory, there are chances that the data it needs might not be fully present on this executor. So it needs to move data across the cluster in order to bring the relevant data into this executor. Yeah. And this is going to happen to all the executors within the cluster. So that is one reason why it is going to increase the network traffic. Now the last disadvantage is reduced data locality. Now we know that each of these executors have a small amount of memory, right? So the amount of partitions it is going to be able to load in this memory is also going to be small. So the number of partitions which are local to this executor will therefore be small. So because this memory is small, the amount of partitions that could be loaded into this memory is also going to be small. Let's say it need P10, it would need to load this in this memory, and P10 is not local to this executor, right? And the reason why it's not local, because it couldn't be loaded into this memory because the memory itself was small. So this leads to a reduced data locality. Yeah. So these are the overall advantages and disadvantage of both thin and fat executors. Yeah. Okay, now that we've seen the advantages and disadvantage of a fat and thin executor, let's try to understand how do we size or how do we create an optimal executor. Yeah. And there are a few rules that we should always keep in mind when trying to size an optimal executor, and there are four of them over here. The first one is leave out one core and 1 GB of RAM for Hadoop, Yarn, and operating system processes, right? So you always leave out one core and 1 GB of RAM. Yeah, this is the first one. Now the second one is the Yarn application master. Now Yarn application master is basically the one which is responsible for negotiating resources to the resource manager. So the application master basically negotiates for resources from the resource manager. So basically, when you say that I want to create an executor with 11 cores and 47 gigabytes of RAM, it is this guy who is going to go and ask the resource manager that I need these resources in order to be able to provision an executor. Yeah. So we also need to leave out something for this guy to function properly. So you can either leave out one executor or you can leave out one core and 1 GB of RAM. The reason why we have two options over here is because application master generally works quite well with one core and 1 GB of RAM. Yeah. But just for simplicity, you may just want to remove out one executor. But this may not be very suitable for cases where you have a fat executor. Yeah. So in fat executors, you have configurations like 11 cores and 47 GB of RAM. You wouldn't want to give away such a big executor for an application master which just needs one core or and 1 GB of RAM. So if your executor is small, just subtract one executor when you define the num executors, right? When you define the num executor, just subtract one executor. We are going to look at these examples. So either you can just subtract one executor, or you can spare out one core and 1 GB of RAM. So that's the second important thing to remember. The third one is 3 to 5 tasks per executor. And we've discussed earlier that the HDFS throughput deteriorates if we have more than 5 cores per executor. It leads to a lot of garbage collection. So, a general rule of thumb, and this is a general practice rather than just saying HDFS throughput, this is a general good practice to have 3 to 5 cores per executor. Yeah. And the last one is when you define your executor memory, right? When you define your executor memory, this executor memory should exclude the memory overhead. So the overhead memory, as we discussed in one of my last videos on Spark memory management, this is basically used for internal system processes, right? So we need to spare out some memory. So the actual executor memory should always exclude the overhead memory. And we are going to look at an example taking into consideration all of these rules. So don't worry if this sounds intimidating right now. Yeah. Okay, so now let's go ahead and try to understand how would we size an optimal executor, right? So let me quickly iterate. We have a 5 node cluster and each of those nodes have 12 cores and 48 GB of RAM. So let's go through the rules that we just walked through and follow each of them. Yeah. So the first one that we saw was we leave out one core and 1 GB of RAM for Hadoop, Yarn, and other operating system processes, right? So we would do the same over here. We would leave out one core and 1 GB of RAM for Hadoop, Yarn, and other operating system daemons, right? And this is basically done per node level. So it's quite important to understand that this is per node. Per node we have to leave out one core and 1 GB of RAM. So per node, after subtracting this, we are left with 11 cores and 47 GB of RAM. Yeah. So this is the amount of resources that we would be left with. Now let's go ahead and follow the second rule. The second rule was that we leave out either one executor or we leave out one core and 1 GB of RAM for the application master. And this is at the cluster level. So it's important to note that this is at the cluster level. This was at a node level. So let's go ahead and do those calculations. So before doing that calculation, let's first calculate the total memory that we have. The total memory that we have is per node we have 47 gigabytes and we have 5 nodes in total. So this is going to be 47 into 5, which is going to be 235. The total cores, the total cores is going to be 11 core in one node and we have 5 nodes, so it is going to be 55 cores. Yeah. Now this is the resources that we have at a cluster level. So now we would simply go ahead and follow this rule, which is the subtracting out either one core, 1 GB of RAM or one executor. So we'll go ahead with one core and 1 GB of RAM. Yeah. So we subtract out 1 GB of RAM, which gives me 234 gigabytes, and I subtract out one core, which gives me 54 cores. So this is the configuration of my cluster. Yeah. So now what I need to do is I need to find out how many executors I need to create and for each of those executors, what are the cores, the number of cores, and the memory that I should be allotting per executor. Yeah. So the first thing that is very simplified is we can find out the number of cores by simply following one of the rules. So we already had these rules which would say that we should assign 3 to 5 cores per executor. So this should be cores. Yeah, it's interchangeable, cores or tasks, because one core would process one task. So cores per executor. So I would simply say that for each executor I am going to assign 5 cores, and this is going to help me find out the total number of executors. So the total executors is simply going to be the total cores, which is 54 cores, by the cores per executor, and this is simply going to be giving me some number which is close to 10. So I'm going to have 10 executors, and each executor is going to have 5 cores. Yeah. So the last calculation that I now need to do is to find out the memory per executor. So in order to find out the memory per executor, I simply need to take the total memory, which is 234 gigabytes, and divide it by the number of executors, which gives me somewhere close to 23.4 gigabyte. So each executor is going to have 23.4 gigabyte. But remember this rule, remember the last rule that we are yet to follow, was that we need to subtract the overhead memory from the executor memory, and that will be the actual executor memory, and this is the calculation for it. So it's maximum of 384 MB or 10% of whatever executor memory we have. Yeah, so let's go ahead and do the calculation. So the actual memory per executor is simply going to be 23. So let me just round this off to 23 GB. 23 minus maximum of 384 MB, or 10% of 23 GB is 2.3 GB. Yeah. So 23 minus 2.3 GB, and let's also round this again to 20 GB. Yeah, so we've rounded it down to 20 GB. So this is the actual memory per executor. Yeah, so we finally found out the number of executors, the number of executors are 10, and let me just highlight this quickly. So the number of executors, the number of executors are 10. The cores per executor is 5 cores, and the memory per executor is 20 GB. So the number of executor is 10, the executor cores is 5, and the executor memory is 20 gigabyte. Yeah. Now a possible question that you may have is, why are we not talking about the size of data? The size of data. Why are we not talking about, let's say we are processing 10 gigabytes of data over here or 100 gigabytes of data over here? Wouldn't the sizes of data affect all of these calculations that we are doing over here? Yeah. So the reason why I'm not talking about the sizes of data particularly is because I want you to focus on one very important metric, which is the memory per core. which is the memory per core. And let's calculate what is the memory per core. So we have cores. The executor core is 5, and 5 cores are getting 20 gigabytes of memory. That means one core is going to get 20 by 5, which is close to 4 gigabytes of memory. Yeah. So that means one core is simply going to get 4 gigabytes of memory, and one core can process one partition, right? That means as long as my partition is less than equal to 4 gigabytes, the processing should happen seamlessly without any issues, right? So whether it's 10 GB or 100 GB, we need to talk about this at a very granular level. What is the size of my partition, right? If my data is partitioned into sizes of 128 MB, into partitions of 128 MB, this configuration that we've created over here is very good, because each core can live up to 4 gigabytes of data. Yeah. So I believe that is how you should be looking at this problem. Try to understand what is your partition size, and then try to figure out that the configuration that you've created, what is the partition that it can process, what is the partition size that it can process, right? What is the memory that has been allocated to each core. Yeah, because that memory would be the amount of data that it would be able to process, right, for one partition. So that was one of the most important reason, but I hope all of this makes sense and it made things clear for you, right? Okay, so to quickly summarize the benefits of an optimal executor, we see that we've tried to maintain a balance between the thin executor and the fat executor, right? So here we see that we have assigned we have assigned 5 cores and 20 gigabytes of RAM in this example, right? Which is not too low and not too high, as we've seen in a thin and a fat executor. So this is a good configuration for good parallelism, right? We also avoid falling into issues with the HDFS throughput, right? Because one of the consequence of this is that it is going to lead to large GC cycles, which is going to pause your program. So we have assigned 5 cores, so this should be good with HDFS throughput. The last one is of course data locality, and we see that the amount of memory is 20 gigabytes of RAM. So the number of partitions this executor can hold, it should be a good number, right? Should be a good number of partitions. So these partitions are going to be local to that executor. So data locality is still preserved, is still enhanced, right? So these are some of the advantages of an optimal size executor, right? Okay, so let's solve one more example to size an optimal executor, right? So this is the configuration of your cluster. Here you have 3 nodes. Each of those nodes is 16 core and 48 gigabyte of RAM. Yeah. So now let's again follow those 4 rules, right? We are first going to leave out 1 core and 1 GB of RAM per node. So once we leave out 1 core and 1 GB of RAM per node, we are going to be left with 15 cores and 47 gigabytes of RAM. And this is per node. Yeah. So now let's calculate the total memory and the total cores that we are going to have in the cluster that we can use. So total cores is going to be 15 into 3, which is 45 cores, and then total memory is going to be 47 into 3, which is going to be 7 3 are 21, 141. Yeah, so this is going to be 141 gigabytes of memory. Now let's go ahead and follow the second rule, which we are going to leave out 1 gigabyte of RAM and 1 core for the application master. Yeah, so let's go ahead and do that. So we are going to leave out one core which gives me 44 cores and 1 gigabyte of RAM which gives me 140 GB of RAM. Yeah, so this is now going to be the resources in my cluster. Yeah, so this is the cluster resources that I can use. So now let's go ahead and find out how many executors how many executors we want to create, and what is the number of cores that we should give to these executor, and what is the memory. Yeah, so let's first find out the cores, right? So again, we are going to follow this and we are going to give 5 executors, and we also see that if we give 5 executors, it is going to, okay, it's not going to fully use 44 cores, right? So instead, let's say we give 4 cores. So if we give 4 cores per executor, we are going to end up with 11 executors. So the number of executor, this is simply going to be total cores by the core per executor. So this is going to give you 11 executors. So I'm going to have 11 executors in total. Each of them is going to have 4 cores. And now let's see what is the amount of memory. So I have a total of 140 gigabytes and I have 11 executors. So this is simply going to give me something very close to 112 point something gigabytes, right? So let's assume it to be 12 gigabytes. So it's going to be giving me some number which is very close to 12 gigabytes. So this would simply mean that the total memory that I would have is 12 gigabytes. Now, if you remember, I also need to subtract out the memory overhead. Yeah. So the memory overhead is again going to be max of 384 MB or 10% of executor memory. So the 10% is going to be 1.2 gigabytes, right? 10% of 12 GB is going to be 1.2 gigabytes. So overhead is going to be max of 384 MB or 10% of 12 gigabytes. And the answer to this is going to be 1.2 gigabytes. Yeah. So let me just assume again, this is, I'm doing this for to make the calculation very simple. So I would just assume it to be 1 gigabyte. Yeah, so now the actual memory is going to be 12 minus overhead memory, which is 1 GB. It is going to be 11 gigabyte. Yeah, so if we were to narrow down the final calculations, it is going to be something like this. Num executors is going to be 11 as we calculated over here. The executor cores is going to be 4 as we calculated over here, and the executor memory is going to be 11 gigabyte. So this is how your calculation is going to look like. Yeah, it's great to see that you've reached the end of the video. So to summarize, we've learned how to size an executor and what are the approaches that you could follow in order to size these executors optimally, right? So we've seen various options like what are fat executors, what are thin executors, what are the advantages and disadvantages of both of them. And then finally, how do you size an optimal executor? What are the rules that are going to govern the sizing of that optimal executor? So I hope all of that made sense, and if it did, please don't forget to like this video, share this video. Thank you so much for watching.